The AP Physics 1 and 2 exams were ridiculously insulting. Let's find out if AP Physics C can bring the goods. All right, a box of mass M slides to the right on a horizontal surface. A small cube, also of mass M, is inside the box. The cube is against the right wall of the box and above the bottom of the box, as shown in Figure 1. Okay, that looks sufficiently difficult. The coefficients of static and kinetic friction between the cube and the wall of the box are mu s mu k, mu s greater than mu k. The speed of the box is decreasing as a result of a resistive force that is exerted on the box. Wow! The resistive force is modeled by F of resistance is negative BV. Okay, well, I asked for difficult problems, and I sure got one on this one. Holy smokes. Consider the motion of the box for the cube the following times. At time 0, the box cube system slides to the right with a speed v naught. So it's already moving with speed v naught, but the air resistance is in the process of slowing it down. And then there's a critical moment. The cube remains in contact with the wall of the box at a certain height, and then the cube begins to slide down. Okay, I will admit that when this printed out, I did have a little look-see, but I have not seen any other page yet. Only this page is all I've seen before I started pushing record. Okay, the magnitude of the normal force exerted on the cube by the wall of the box is Fn. Determine an expression for the magnitude of the acceleration of the cube. Okay, well, can I not just say, here we go, AI, can I not just say that for the box cube system, okay, the only unbalanced force is negative BV, and so that's going to equal MA, but the total mass is actually 2M, so that's the mass of the entire system times acceleration. They want just the magnitude. Okay, so screw the negative and the arrow, and then you just get A equals BV over 2M. Now, how do I know this is easy? Because they use the word determine. Determine means just give me the answer. It does not mean they really care about any work. Okay, I'm sorry. I should probably actually read it. So for the cube, for the cube, the only force is the normal force. So the cube has force normal, mg, and friction, which cancel out. So yeah, it's just force normal equals ma. That's just the cube. I was looking at the box cube system. I'm sorry. I should look at the in terms of. So force normal over m. So that's why it is a determine. And I'm trying to write capital M because I think that it needs to be the same case. So I can't put lowercase m. Okay, derive. That means there's going to be some steps. An expression for Fn is a function of t from t equals 0 until immediately before the cube reaches the bottom of the box. It's a function from t from t equals 0 until immediately before the cube reaches the bottom of the box. Okay, so I think, so the reason why I'm giving pause here is because I thought that they were asking for something that involves a piecewise function, right? Like these two, but I actually take it back. The force normal, actually, okay, so let's see it again. There's the force normal right there, okay? This force normal will be the same regardless whether the box is standing still or lowering until it touches the floor. Then there will be two force normals, okay? Until immediately before the cube reaches express your answers in terms of all this. Begin your derivation with the fundamental physics principle. Okay, so what I'm going to say is I'm going to say this. Now I'm going to look at the box cube system. So negative BV equals 2M times A. Okay? And it's really going to be negative BV equals 2M times A is dV dt. I wonder how many students even thought to do this. So now I'm going to do negative B over 2M. I divide by 2M times dt. I bring the dt up equals dV over V. All right, I hope I'm not doing this like super difficult, like some kind of a psychopath. Okay, negative b over 2m t plus a constant equals natural log v. So then v is equal to e to the negative b over 2m times t plus a constant, which is the same as time, which is times a different constant, right? Okay. So now I'm going to say that V equals V naught. We were told. V naught. Okay, there it is. At t equals 0. So if I say v naught is equal to c e to the 0, then c is equal to v naught. So here we go. So v equals c e to the minus b over 2m times t. V naught. I solved for the c. All right, so now I did all that work just to get to this. Now, the next thing I'm going to say is I'm going to say this. I'm going to say that, what am I going to say? Oh, I'm going to say that force normal is equal to ma of this cube, of the cube only. Well, this is the v of the cube. If v equals v naught e to the minus b over 2m times t, then acceleration, which is dv dt, is going to equal negative b v naught over 2m e to the minus b over 2m times t. So there's the acceleration. And then, yeah, all I have to do is just multiply by m, which just cancel out that m. So the normal force will be negative b v naught over 2, and then doing ma, and then that m right there nukes the m's, b over 2m times t. All right. That uber sucks. All right. On the axis shown in figure 2, sketch a graph of the magnitude F friction of the frictional force exerted on the cube by the wall as a function of time t. Okay, get ready for it. You ready, folks? Flat line! Decaying exponential! Why? Because when this not slipping, at the moment you're not slipping, then the friction force is exactly equal to mg. But wait a minute, is it friction force equal to mu force normal? And then the force normal is exponentially decaying. Yes, it is. Okay, so that would be like this. That's not an asymptote. I'm sorry. Exponential decays don't have an asymptote. Vertical asymptote, I mean to say. Yeah, but it's actually friction is less than mu force normal. Here, the friction is exactly the same as mg until the moment that the slipping begins. Then when the slipping begins, it becomes equal, and then force normal is exponentially decaying, so the friction is also exponentially decaying. Derive an expression for T critical in terms of all that bull crap as appropriate. So when force friction static is exactly equal and not greater than or equal to mu static force normal is when T critical is. Now, force friction static is exactly equal to mg at this moment, okay? And I need to be using capital M, sorry, okay? That's the mg of the cube. So I'm going to say this. I'm going to say the mg of the cube equals mu static. Now, what was force normal? It was, and ignoring the negative, b v naught over 2 e to the minus b over 2m times t. Are these all things I'm allowed to have? I'm allowed to have b, v naught, 2 is a fundamental constant, m is allowed to be my answer, g is a fundamental constant. I think I have everything I need. So now I need to just solve for t. This is going to blow balls. 2mg, bring the 2 up. b v naught mu static. Bring all that stuff down. E to the minus b over 2m times t. So then this is going to be natural log of 2mg over b v naught mu s equals negative b over 2m capital M times t. Okay, so you can nuke the negative by flipping the inside of the logarithm. B v naught mu s over 2mg makes this the negative of what it was before, so this would just be b over 2m times t. So then the t critical moment will be 2m over b, that's solving, natural log of b v naught mu naught over 2mg. I would go ahead and say that this is probably the hardest question on AP Physics C Mechanics I've seen in my entire life. What the okay? All right, that was not okay. Well, I asked for it and I got it. A projectile of total mass 4m is launched from ground at position x equals 0, time equals 0. The projectile is launched with initial speed v naught at an angle theta above the horizontal. Great, I'm fine with that. When the projectile is at the highest point in its trajectory, it breaks into 2 pieces. Great. Q and R of masses m and 3m respectively. The motion of the projectile is described at the following times. At time t1, Immediately after the projectile breaks apart, the two pieces are moving away from each other horizontally. At time t2, piece Q reaches the ground back at x equals 0. So he just goes right back where he came from, okay? And then piece R is over here, okay? Really what I want to do is piece out. Okay, the horizontal and vertical components of the momentum vector are represented by px and py respectively. The shaded bars in figure 2 represent px and py of the projectile immediately after t equals 0. So this is not when it was at the highest point. At time t1, immediately after the projectile breaks, when the projectile is at the highest point in its trajectory, it breaks into pieces Q. So that's at the highest point. So this is at time equals 0. That's the launch. And then at time t1, there's no y momentum for anybody. Draw shaded bars to represent px and py of piece Q to time 1. Start the shaded bars at the dashed line that represents 0 momentum. Represent any momentum component that is equal to 0 by drawing a distinct line. Okay, so there's going to be no momentum vertically because you're at the highest point, and that means you have no up or down motion. Okay, and then I got to be really careful here because this has a mass of 4m, and this has a mass of only 1m, but he has the same speed as he had right before. So his Vx and his Vx are the same because he lands right back where he started from. So he has the same x velocity. But he has 1/4 as much mass, and he's going to the left. So this guy, piece Q, is going to get 1 out of 4 momentums to the left. And then to balance this, I have to have -1 plus something makes 4. So this has to be +5. Okay. Derive an expression for x2 in terms of v0, theta, and physical constants. I will do it right here. Okay, so at the moment of launch, your Vx is equal to V0 cosine theta. That's your Vx, okay? Okay, and then this is going to be Vy is V0 sine theta, okay? At what time do you reach your highest point? I feel like that's important to know. So I'm going to say Vy, this is V0 y and V0 x, equals V0 y plus the acceleration of gravity is negative and downward t h. I'm calling that T1. I'm going to call that T1. That's what they call it. They call it T1, so I'm calling it T1. Okay? So the Vy at the top is 0 because you're at the highest point. So V0 y equals gt. So T1 is V0 y over g, which is V0 sine theta over g. Okay, that is the time it takes to reach the top. It takes the same time to land at x equals x2. Okay, does that make sense? Now, where is this location? Where is this location? This location is going to be V0 x times t1. So this distance, which I'm going to call x1, is V0 x times t1. But now what I want to know is how far is it from here to here. And so to do that, I'm going to say the time, so I'm going to say x2 minus x1, that's this distance, okay? That's this distance is equal to V0 x, something times t. But what is the velocity of this piece? The velocity of this piece is going to be what? Let's see. You've got 4m times V0 x, that's the initial sideways momentum, equals negative m V0 x plus 3m naught. I'm going to call it v final x for him, okay? So then if I bring this over, it's 5m V0 x, which explains that bar 5 right there, equals 3m naught v final x. So then the v final x is 5/3 V0 x. So I'm going to say x2 minus x1. What was x1? V0 x times t1 is equal to 5/3 V0 x times t1. So then I'm going to add over, I'm going to make it, what, 8/3? So x2 is V0 x times 8/3. What am I allowed to have in my final answer here? Oh, times t1. Okay, well, this is t1, V0 sine theta. Okay, so here we go. So x2 is going to be 8/3 times V0 x oh, that's V naught cosine theta, okay, V naught x, times T1, which is V naught sine theta over G. So then you can say 8 V naught squared sine theta cosine theta over 3G. Or if you want to take a factor of 2 over here and make him 4, then it would be 4 V naught squared sine 2 theta over 3G. What the fuck? Okay, sheesh. They don't mess around in AP Physics C mechanics. Okay, the horizontal component of the velocity vector, of a velocity vector is represented by Vx. Figure 4 shows the horizontal component Vx cm of the velocity of the center mass of the projectile as a function of time. During this interval, on Figure 4, sketch a line or curve to represent Vx as a function of t for the time interval for each of the following. Seriously? All right. So we need to label. So the Vx of the center mass is the same. The center mass does not change its motion. So Vx of the center mass is still the same because there are no external horizontal forces. Now, what about the Vx of piece Q? We said that was going to be this way, and it's the same speed. It's the same speed, so he lands right back at the same place. So that's going to be Q. And then this guy gets 5/3. So this is going to be, and then, okay, and then this is going to be Vx of P. Is that what you? No, P's R. Sorry, R. And then this is Vx of Q. Hey, is that what you wanted? I don't even know. Consider a case in which the projectile is launched at the same angle and initial speed as initially described. When the projectile breaks into Q and R, Q falls straight down. In this case, piece R reaches the ground at a new X. The new X is less than X2. Why is that? Because now the Q doesn't have negative momentum in the X. It has 0 momentum in the X. Okay, the Q doesn't have negative but 0 momentum in the X. So that makes Q have more momentum in the X in this new case. But the total momentum in the X is the same as before. So R has less momentum in the X to make the same sum and less horizontal speed. So it's going to go less distance. All right. Okay, a horizontal spring of known spring constant K is attached to a wall. The block of known mass is placed on a horizontal surface next to not attached to the spring. The spring is at its relaxed length when the block is at position x equals 0. Okay. All right, there's friction between the block and the surface only for x greater than 0. A student is tasked to experimentally determine the coefficient of kinetic friction between the block and the surface using a graph, but we know the spring constant, okay? The student's permitted to use only measurements from a meter stick. Okay, so what quantities are we going to measure? We're going to say x is the distance the block is pushed to the left from x equals 0, and d is the distance the block slides across the frictiony surface as after release from the spring compression. Okay, what's a method to reduce experimentally uncertainty? Repeat trials, but many different values of x, different values of d, which is what that will result in. Okay, indicate what quantities the student could graph. Okay, so what I'm going to do is I'm going to do this up here. This is an energy situation. Your spring energy is going to become energy dissipated. 1/2 kx squared becomes energy dissipated. So that's going to be friction force times the sliding distance. Friction force is mu force normal, and that's going to be mu mg. Okay, so 1/2 kx squared equals mu mg d. So So I think I'm going to plot D on the vertical, x squared on, I do this lab with my students, I do it with them in P1, x squared on the horizontal, okay? So I just said 1/2 kx squared equals mu mgd. So if D is on top and x squared is on the bottom, then it looks like we're going to have k over 2 mu mg, okay? So slope is k over 2 mu mg. Set the slope equal to k over 2, oh, you can't even see half of this, mu mg, and solve for mu. And then I'm going to go back and I'm going to make sure they all say mu k, because that's what it said, and I want to make sure I have the exact same subscripts and things. Oh, what do we got now? What are we trying to do? What are we trying to do? Get a spring constant. Okay. In a different experiment, the student is asked to determine the spring constant of a new spring that's attached to the wall. The block of mass 2 kilograms. The surface, the slope's upward. The student pushes the block and presses the spring at distance s. Blocks released from really. I mean, it's just basically the same procedure I had before. You just gave them the answers to A and B, a-holes. Okay. Student uses a meter stick to measure the maximum height h. The student's measurements of S and H are shown. It does say it's completely frictionless, doesn't it? It does say it's complete, where no frictional force. Okay, so the story's going to go something like this. So we're going to say that 1/2 k, this distance, S squared becomes mgh. So then what I'm going to do is I'm going to say H over S squared is equal to K, H over S squared is equal to K over 2mg. Okay, so here we go. This is going to be our rise. This is going to be our run. This is going to be our slope. So what I'm going to do is I'm going to plot S squared. S squared and meters squared. Oh, this is going to be super easy. Okay, let's get rid of this shite from AP pre-calculus that I recorded just a few minutes ago. 0.02, 0.04, 0.06, 0.08, 0.1. Now, all those are going to get squared. All right, so 0.0004, 0.0016, 0.0036, 0.0064, 0.0100. Okay, and then my heights will be 0.02, 0.04, 0.13, 0.18, and 0.33. Okay, so let's get rid of that. Let's turn on plot 1, zoom 9. Okay, let's do a linear regression, L1, L2, and let's store it into Y1. Okay. Hooray. All right, so now I'm going to plot this. Okay, quantity. It was going to be H in meters, and it's going to be S squared in meters squared. Okay, that's what we're going to do. So let's see. Let's trace this SOB. All right, so I'm going to go out to 0.01. So if this is 0.01, oh, no, that's not going to be 0.01. 1, 2, 3, 4, 5. 0.01. 0.002, 0.004, 0.006, 0.008, and then 0.01. Okay, so then can I let's see, the X min, the X max is going to be 0.012, okay, because that's this over here, and the X scale is going to be 0.002, and you could do all this in Desmos. Oh, what are my heights going to get up to? 33. So 5, 10, 15, 20, 25, 30. That's not good enough. I'll just go up to 50. So 0.05, 0.10, 0.15, 0.20, 0.25, no, I didn't mean that. I meant 10, 20, 30, 40, 50. Never do your AP exam. 60. Never do your AP exam in pen, but mark real dark. Okay, mark real dark. Hey, so 0.6. X scale is going to be 0.1. Let's just turn the grid on. Okay. All right. So I'm gonna trace. I'm gonna plot a graph. And what do I get right here? I get 0.33, which is just above. Yeah, sorry, folks. Okay, sorry, AP readers. It is just above halfway, so you have to take it, okay? It's just above halfway, so you have to take it. 0.18, which is about right here, and then 0.0064, which will probably be about right. right there, sorry, okay. And then 0.0036 should be right here, and 0.013, which would put us about right there, okay. And then 0.0016 put us about right there, and 0.04 is about right there, and then like really tiny, and then really tiny. Okay, so let's see. Do I have my straight edge? Let me find my straight edge. I had a straight edge. Where did I put my straight edge? I want a straight edge. I want to actually make this look good. Oh, here it is. Okay, I'm going to take my straight edge. I'm going to try and make this look good. Okay, all right. All right, use the best fit line. So what did I say before? I said that the slope is equal to k over 2mg. So then what was the slope even? 31.952 is equal to k over 2. What was the mass again? 2 kilograms. And you can use g equals 9.8 or 10. They do not care. They just want to see that you're doing something that makes some sense. 952 times 2 times 2 times 9.8. And your spring constant is, wow, 1252 newtons per meter. Okay, well, whatever. So I don't even think this ever took place for real. Okay, what we got here is a unicycle is placed on a stand such that the wheel does not touch the ground. The rotational inertia of the wheel about the axle is IW. One end of the crank arm can be attached to the wheel. Okay, shown the side view. Scenarios 1 and 2, crank arms of different lengths are connected to the wheel. In each scenario, the wheel is initially at rest. Force is exerted at the end of each crank arm. The direction of the force remains perpendicular to each crank arm at all times. So that's just torque. The mass of the crank arm is negligible. Scenario 1, the length of the crank arm is L1. And the angular speed of the wheel immediately after the crank arm has been turned through one rotation is omega 1. It's longer. It's omega 2 through one rotation. Okay, well, it's a longer length, so omega 2 is greater than omega 1. Okay, and so here's what we're going to say. We're going to say more distance the force is applied means more torque, right? Okay, more torque means more angular acceleration. And if omega squared equals 2 alpha theta, and the theta is the same, right? One rotation, okay? Then the omega is greater in case 2. Okay, more distance in case 2. So more torque in case 2 is what I mean to say. It means more alpha, okay? So omega is greater in case 2. All right. Derive an expression for the angular speed omega 1. This is such an AP Physics 1 question. So the first two questions were terrible, but these two are really, these last two could have been AP Physics 1 in my opinion, okay? The only thing that made this one a little tricky is that they did not derive this equation for you, but it should have been a pretty easy question to derive. Sometimes they just give you the equation straight up. Okay, so what am I going to say? Express your answers in terms of the eye of the wheel, the force L1, and physical constants. So we're going to start with torque equals I alpha. Okay, so the torque is going to be L1 times the force, which is no sine theta because it's perpendicular, IW times alpha. So alpha is L1 force over I of the wheel. Okay, now I'm going to say omega 1 squared equals 2 alpha theta, with theta being one rotation, that's 2 pi. So omega 1 squared is 4 pi alpha, because that's plugging in the 2 pi. So then let's plug in the alpha, 4 pi L1F over IW. Sorry, okay? Yeah, that's a Freudian slip. Okay, so omega 1 will be the square root of 4 pi L1F over IW, and I think that's all there is to that. Okay, in scenario 3, the unicycle is placed on the ground, such that the unicycle can move forward without the wheel slipping on the ground. A force of the same magnitude F is exerted at the end of the crank arm of length L1 as in scenario 1. The direction of force remains perpendicular the whole time. Resulting angular speed is omega 3, which will be less than omega 1, okay? So here's what I'm going to say. I'm going to say, now in this case, there is another force of friction producing torque. So in other words, with this being the crank arm, that was the F before, but now there's also a force friction. How do you think that the unicycle accelerates forward? Here's a free body diagram of the unicycle. mg, force normal. How does he accelerate? How do you accelerate forward? You need friction. Now, here is the extended body diagram. Here's your mg, and there's your force normal coming out of there. Okay, right? And the force, okay, so, oh, and then you have that external force also, which changes its motion, so its direction. So that external force will change. But here's the bottom line. The bottom line is that there's another force of friction producing torque. The force friction produces torque opposite F's torque. Okay. So the force friction produces torque opposite F's torque. So the force friction, so the net torque is less, the alpha is less, right? Okay. And so if omega 1 equals the square root of 4 pi L1 F over I omega, so this becomes, actually, it actually becomes like F minus F friction, if they're both at the same distance, right? So less numerator, less omega. All right, well, let that be a lesson to you. Don't start question number 1. Start with a different question. In AP Physics nowadays, question number 1 is usually the hardest, and it will demoralize you.